this has to be a long lecture. When I picked up the pack of paper that I'm going to lecture off of, it was thick. So at least a three-parter. Hopefully we can keep it to that. This is a new concept that is confusing for students. Like the increasing and decreasing concepts that we did in section 3.1, that's, going up and going down. That's not really new. I mean, maybe a new way to think of it, but not really that new. Concavity maybe is new. So in this section, we cover concavity of the graph. And I tried to do an explanation of the concept of concavity and wrote some words down. But again, my English ability is not so great. Anyways, so if a region of graph is not a straight line, we say that graph in that region is either concave up or concave down. The graph is concave up if the region opens up. The graph is concave down if the region opens down. Clearly not that great of an explanation. Here is an image of what I'm trying to say. And an important thing is concavity has nothing to do with increasing or decreasing. It's completely independent. So a function can be concave up and increasing. It can be concave up and decreasing. It can be concave down and increasing and concave down and increasing. So here, this is an example of a decreasing graph because I'm moving from left to right, it's going down. And this, I say, opens up. This little bend right here that I'm going to exaggerate, this makes the graph concave up. In some sense, I don't know. I usually say water would stick in this, but maybe in this little area there it might. So that's concave up but decreasing. This is an increasing graph, and this little area there makes it concave up. This little bend to it makes it concave up. So this is decreasing, but a little bent upwards. Increasing, bent upwards. And there's pictures of concave down and decreasing. So there's concave down, concave down. So concave up is kind of that. And down is kind of that, pictorially. And again, you could be concave up and decreasing. You could be concave up and increasing. You could be concave down and decreasing. You can be concave down and increasing. Concavity has nothing to do with increasing and decreasing. When we sit in the world of graphing, we're going to, in this section, need to identify regions of a graph that are concave up, regions of a graph that are concave down, and then something called an inflection point. In 3.1, we did maximum points and minimum points, which were different. But in this section, we're going to do inflection point. An inflection point is just where a graph changes concavity. Here's an example of an inflection point where a graph is increasing. It goes from concave down to concave up. This point where the graph changes from concave down to concave up is referred to as an inflection point. Here's another example. A graph is decreasing. First it's concave down, then it's concave up. The point on the graph of a function where the graph changes either from concave down to concave up or from concave up to concave down is called an inflection point. Technically, if I want to give a technical definition, which I wrote here, which is maybe a little bit too much, a point is called an inflection point if the graph is continuous, it doesn't have a whole jump or asymptote at the point, and the graph changes concavity. So as long as the graph changes concavity and the point's a point on the graph, it's probably going to be an inflection point. So I made a picture here just to try to help us understand the intervals for graph where a graph is concave up and concave down. I made the concave up region blue, the concave down region some sort of red. If I wanted to describe where a graph is concave up and concave down, I'm going to do it just like I did when I tried to describe an interval where a graph is increasing and decreasing. The point that's labeled here, where it changes from one concavity to another, is an inflection point. That point 1, -3, I call an inflection point. And usually, I don't like writing inflection point over and over as I lecture in this section. Usually, I default to just doing IP, to mean inflection point. And then to describe the regions, the intervals, this first interval goes from the far left edge of the x-axis, which has an x-coordinate of -infinity, to the x-coordinate of the inflection point, which has an x-coordinate of 1. The second interval goes from the x-coordinate of the inflection point, which has an x-coordinate of 1, to the far right edge of the x-axis. This interval, it goes decreasing and increasing, so it's both increasing and decreasing. The second interval, it's both increasing and decreasing. In the first interval, the graph is concave up. You can kind of see where the water might puddle there. In the second region, the graph is concave down. This is just by inspecting. If I draw the graph clear enough, you should be able to know what the inflection point is and tell whether the region to the left of the inflection point is concave up or concave down. Similarly, tell whether the region to the right of the inflection point is concave up or concave down. And I just wrote this interval is this graph is concave up in the interval from negative infinity to 1. It's concave down in the interval from 1 to infinity. So I wrote up a make-believe example because I don't think students understand concavity and how it might, come up in a quasi-realistic problem. So I made just a short word problem, and I said a company produces a component for cell phones. Due to enormous demand, the company has been able to raise the price of the product every year for the last 8 years. The table shows the price the company's charged for the component each of the last 8 years. So in year 1, $10 for the component, then $11, $13, $16. They keep raising it, and finally in year 8, they're selling it for $19.75. You'll see that the price of this component for the cell phone goes up every year. It went from $10 to $11, keeps going up. It never goes down. So if I graph this, and when I graph this data, this is going to be a strictly increasing function. Let me show you a graph of the function the best I can. I might have to zoom in. I had a really tough time getting these points to graph and to so this is a picture of the graph of that data, and I had my Desmos connect each point. So you can maybe see that the graph is increasing, and then here, for the first 4 years, the graph of this function is concave up, and then after the 4th year something happens and the graph of the function is now concave down. So I plotted the points, connected them with lines, and you can see hopefully that part of the graph is concave up, part of the graph is concave down. The price of this component is going up the whole time, so the graph is increasing the whole time. First it's increasing in concave up, then it's increasing in concave down. Let me show you visually, or in my table, why that inflection point happens there at the 4th year. So I took the data that gave me the year and the price in dollars, and you can't see that yet, I made this too big. And I made a third row. That third row, just won't go that way, is the amount of price increase each year. So in the first year, it went from $10 to $11, the price went up $1. In the second year, it went up from $11 to $13, it went up $2. Then $13 to $16 increased by $3. Then $16 to $18 increased by $2. $18 to $19 increased by $1. $19 to $19.50 increased by 50 cents. $19.50 to $19.75 increased by a quarter. So what happens, year 4 is the year where look at how the prices are going, the amount of the price increase is going up, and then all of a sudden the amount of the price increase starts going down. The price is still increasing, but not increasing as much as it did before. The reason this graph that you can never see here has an inflection point at year 4 is because this is when the amount of the price increase starts decreasing. The price is still going up, but it's going up by a smaller amount each year. For the first half of this, the amount of the price increase gets bigger and bigger. Then the amount of the price increase gets smaller and smaller. That's what an inflection point can show up in a realistic-ish kind of problem. So even though the price is increasing the whole time, while the amount of the price increase gets bigger than the last year's price increase, you get concave up. When the amount of the price increase is less than last year's price increase, you get concave down. So that's not really for homework, but it's just to maybe help you understand concavity better than you might have otherwise. So in this section, we're going to do all the concavity using calculus. We're going to need to find intervals where a graph is concave up. We're going to need to find intervals where the graph of a function is concave down. And we're going to need to find inflection points. Turns out that finding these intervals and inflection points is perfectly identical to what we did in section 3.1 to find the intervals where graphs are increasing and decreasing. But instead of doing the work with the first derivative, we do the work with the second derivative. So the graph of a function is concave up if the value of the second derivative is positive in that interval. The graph of a function is concave down if the value of the second derivative is negative. Just like we did, a graph is increasing in a region where the first derivative is positive. A graph is concave up in a region if the second derivative is positive. Just like we did, the graph of a function is decreasing in the interval where the first derivative is negative. The graph of a function is concave down in a region where the second derivative is negative. So for increasing and decreasing, it's first derivative. For concavity, it's second derivative. And I tried to show this in a table, but I almost think I shouldn't show it. But this picture right here, this is a picture of a graph that's decreasing, which means the first derivative is negative because it's decreasing, but it's concave up. That means the second derivative is positive. This next graph is increasing, which means the first derivative is positive. And it's concave up, so the second derivative is positive. These bottom graphs are both decreasing. This is decreasing, this is, this guy right here is decreasing. So the first derivative is negative. It's concave up, so the second derivative is positive. This function right here is increasing, so the first derivative is positive. It's concave up, so the second derivative is positive. This graph is decreasing, which means the first derivative is negative, and it's concave down, which means the second derivative is negative. This graph is increasing as I go from left to right. So the first derivative is positive. My paper is bouncing back at me, making it hard to write. And it's concave down, making the second derivative negative. So this is important in terms of this section and section 3.4. Decreasing, first derivative negative. Concave up, second derivative positive. Increasing, first derivative positive. Concave up, first derivative positive. Decreasing, first derivative negative. Concave down, second derivative negative. Increasing, first derivative positive. Concave down, second derivative negative. That's kind of the whole ball of wax right there. That's the big concepts between sections 3.1 and 3.3 jammed together in a table. That's important to at least conceptualize. I can do a lot with not understanding, and you know, if you understand this, you're in a better position than I would have been as a calc student. I don't know why this is so bumpy right now. I need the surface to write on, otherwise the videos look strange. I'm looking at some of my other videos. I know that this is a good idea, having this white background. So how are we going to figure out the intervals where a graph is concave up? the intervals where a graph is concave down, and the inflection points, super easy, almost identical to the first derivative test. I find the second derivative, I find the critical numbers for the second derivative, which are any values that make the second derivative 0 or undefined. Just like I did with the number line for increasing and decreasing, I plot the critical numbers on a number line that has negative infinity and positive infinity as well. Create my intervals. I do test numbers. After I plug the test number in, I look at the sign. If I get a positive sign, the graph is concave up in that interval. If I get a negative number, the graph is concave down in that interval. And I determine if the critical point is an inflection point. A critical point is an inflection point if it changes concavity and it's continuous at the point. And if I have an inflection point, the algebra only gives me an x. I'll need to get the y. So let's go through these steps with this problem and let me mark it up. So to figure out where a graph is increasing and decreasing, first I'm going to find the second derivative. So for this function, my first derivative, the derivative of 2x cubed is 6x squared. The derivative of minus 12x squared is minus 24x. The derivative of plus 5 is 0. That would be useful for increasing and decreasing, not useful at all for concave up or concave down. So now I'm going to do the second derivative. The derivative of 6x squared is 12x. The derivative of minus 24x is minus 24. So I have my second derivative. Once I have my second derivative, I'm going to get the critical numbers for the second derivative by setting this one equal to 0. So this is my second derivative. Now I'm going to get my critical numbers. If it was a fraction, I'd have to set the numerator and the denominator separately of the fraction equal to 0. But it's not. It's just a nice polynomial. So I'm going to set the critical numbers, the derivative, second derivative equal to 0, and do the algebra to get my critical number. So my critical number is going to be x equal to 2. There aren't separate types of inflection points, like maximums and minimums are different kind of first derivative points. Inflection points are only one kind, whether it goes from concave up to concave down or concave down to concave up, we just call it an inflection point. So going through my work here, I found the second derivative, I found my critical numbers. Now I'm going to plot them on the number line with the infinities and create intervals. So my number line is going to go from negative infinity to positive infinity with a 2 between, and I'm going to create the interval negative infinity to positive 2 to infinity, no different than the first derivative test. Pick numbers. Here maybe I'll pick 0, there I'll pick 3. 0 because it's an easy number, and 3 because it's up close to the edge. So created my intervals. Now I'm picking numbers. I'm going to plug them into the derivative. Graph is concave down if I get negative. Graph is concave up if I get positive in that interval. So now let me do f double prime, second derivative, evaluated at 0. So I'm going to go 12 times 0 minus 24. That's going to come out to minus 24. The fact that it's negative doesn't mean the graph is decreasing. It means the graph is concave down. I don't know if it's increasing or decreasing. It could be either. And then in the next interval, I'm going to plug in 3 into the second derivative and do 12 times 3 minus 24. That gives me positive 12. And again, it doesn't mean it's increasing. It doesn't mean it's decreasing. Positive into the second derivative means it's concave up. Negative into the second derivative, it's concave down. So when I go to answer the questions, find the intervals where the graph is concave up. It's concave up in the interval from 2 to infinity. Find the open intervals where the graph is concave down. It's concave down in the interval from negative infinity to 2. Because it's changing concavity and the graph exists or is continuous at x equal to 2, I have the x coordinate of the inflection point and I don't have to separate it into a special kind. Now I just need to get the y-coordinate of my inflection point. So to get the y-coordinate of my inflection point, I have to use the original function. I'm going to get y equals to 2 times 2 cubed minus 12 times 2 squared plus 5. And that's silly to try to do in my head. So 2 times 2 cubed minus 12 times 2 squared plus 5. The y-coordinate of my inflection point is negative 27. So the inflection point is going to be the point x equal to positive 2, y equal to negative 27. So the algebra is not particularly hard. It's exactly the same algebra, except I'm using the second derivative, making slightly different interpretations, but it's basically the same. And that's everything for that example. So now we're ready to start some homework. First, we're going to look at some graphs, and then we're going to do everything by hand. So there's your problem 1. I don't know if that point shows up well enough. Let me autofocus this. I don't know if it's going to make a difference, but you might be able to make a stab at problem 1 with this newly focused picture. I'm going to do my problem 2, just identifying the intervals. This guy right here, assuming it changes concavity as an inflection point. And so I'm going to split the graph on either side of this point. To the left of this point, I go from the far left edge of the x-axis, which has an x-coordinate of negative infinity, to the x-coordinate of that point, which is 1. This is a concave down region. So in my answer for concave down, which is part B, I put this first interval from negative infinity to 1. The next interval starts at the x-coordinate of the marked point, goes off to infinity, and that's a concave up region. So I put that in my answer to part A. Because the graph changes concavity and the graph is continuous there, that point 114 is an inflection point. I don't know if that's good enough, but you might be able to do 3. I'll move on and do 4. So for 4, I'm going to split the graph. The region to the left of the marked point goes from the far left edge of the x-axis, which has an x-coordinate of negative infinity, to the x-coordinate of that point, which is 4. This is a concave up region that decreases, then increases, but it's always concave up. So in my answer to part A, I did negative infinity to 4 for concave up. Once I get beyond this point, I start at the x-coordinate of that marked point, which is 4, go to the far right edge of the x-axis, which is infinity, and this increases, then decreases, but it's always concave down. That region gives me the concave down. Because the graph changes concavity and it's continuous there, that point is an inflection point. This is a hard problem for me to even create the function for, but I like it. Let's do 5 together. These points are going to be inflection points. Let me break this graph up on number 5 to the region to the left of the marked point, the region between the marked points, and the region to the right of the marked points. My first region is going to go from the far left edge of the x-axis, which is x equal negative infinity, to the x-coordinate of that point. This increases, then decreases, but it's concave down. So when I go to write my answer for an interval where it's concave down, this region, or that interval, negative infinity to negative 4, is going to show up. The next region goes from the x-coordinate of the first marked point, which is negative 4, to the x-coordinate of the second marked point, which is 2. And this is decreasing and then increasing, but it's always bent up. This is a concave up interval. My answer to part A of number 5 is going to contain that interval from negative 4 to 2, where it's concave up. And then the last region goes from the x-coordinate of that point that's marked, which is 2, goes past the maximum point and goes down to infinity, works its way to the far right edge of the x-axis. This is all concave down. It increases and then decreases, but it's all bent down. This is a concave down, and it belongs in this part B for number 5. Both of those points, because here, the first point it changes from concave down to concave up, that makes that an inflection point. The second point, the graph changes from concave up to concave down. That makes it an inflection point. And they're not special kinds of inflection points. Inflection points are just what they are. So the point -4, 384, and the point +2, 272 are both inflection points. And we don't even take the time to split the y's and saying the inflection point y value is y equal to 384. We do that for maximums and mins, but not for inflection points. 7, I gave you a W, and I have a corresponding W in 8. And I marked just the inflection points, not to confuse you with the maximums and the minimums. So for number 8, I get the region to the left of the marked point, between the marked points, and to the right of the marked points. My first interval is going to go from -infinity to the x-coordinate of the marked point, which is -1. The graph decreases and then increases, but it's always concave up in that region. So part of my answer to concave up is the first region. The middle region goes from the x point that has an x-coordinate of -1 to a point that has an x-coordinate of +1. Again, it both increases and decreases, but the whole time it's still bent down, it's concave down. So that region from -1 to 1 went in my answer to part B. The third region goes from the x-coordinate of the marked point to, which is 1, to infinity. And again, that decreases and then increases, but it's concave up in the whole region. So I put that in my answer to part A. Both of these points, the graph changes concavity either from up to down or down to up. So both of those points are considered inflection points. For 10, this is evil. I marked the minimum point, but this isn't a change in concavity. I probably shouldn't have even marked a single point, because this point right here, the graph to the left of it is concave up, the graph to the right of it is concave up. A parabola doesn't have an inflection point. It would have to, do something like that, have a bent over hump. This graph is concave up everywhere. It's never concave down. And that point that I marked was a minimum point. Maximum and minimum points usually have nothing to do with concavity. It's a distractor point that I shouldn't have probably marked, but I did. So this graph is concave up from negative to positive infinity everywhere. There is no inflection point. It's never concave down. There's 11, 12. So for 12, I split the graph on 2. 2 is the asymptote. The left half of the graph goes from -infinity, far left edge of the x-axis, to +2. There's no point marked because there's no inflection point. The right part of the graph goes from +2 to infinity. And hope you can tell by inspection that this region is concave up and that this region is concave down. At this point, it's just looking and knowing the difference between what concave up looks like and what concave down looks like. So the first... Whoa. This is backwards. The first region, -infinity to 2, the graph is concave up. The second region, 2 to infinity, the graph is concave down. And there isn't an inflection point because 2 isn't in the domain of the function. There's an asymptote there, and you can't get an inflection point across an asymptote. Put this off to the side so I can fix my mistake. One last one, and then we'll move into our part 2. And it's year 13 and my 14 are kind of the same. I have a vertical asymptote at x equal to -5. I have a vertical asymptote at x equal to +5. And I marked an inflection point that has an x-coordinate of 0. Let me separate the graphs. So the region to the left of the vertical asymptote goes between x equal to -infinity and x equal to -5. That line's drawn for me. I won't draw it again. I'll draw the line through the inflection point. The middle region is going to go from x equal to -5 to x equal to 0. And then between 0 and 5. And lastly, between 5 and infinity. First region is definitely a concave up. The second region looks to me concave down. then it bends up. That's why there's an inflection point there. Then it goes concave up, and then last region concave down. Even though it changes concavity across the asymptotes, you don't get inflection points on asymptotes because they're not in the domain or the graph isn't continuous there. The only inflection point is this point 0, 0 because the graph is connected on either side of that. So if I take these answers, the interval from negative infinity to negative 5 and the interval from 0 to 5, put it in the concave up. The interval from negative 5 to 0 and 5 to infinity, put it in concave down. The negative 5 and positive 5, the graph isn't continuous. It has asymptotes there. I don't get inflection points because there's no point on the graph with an x-coordinate of 5 nor negative 5. But I do have an inflection point at 0, 0. So that's a nice place to stop. There's only a handful of problems left, I think, to get through the section. Yeah, but they're long. So the next, maybe we can do this in 2 parts, but there's only a handful of problems, but they're all doing algebra to find the intervals where the graph is concave up and down and the inflection points.